At the sample problems about the phasor, okay, how we can use the phasor to simplify our calculation. So the first one is about the resistor. Okay, you may consider this is, yeah, you may using the phasor is somehow like overkill, yeah, but yeah, this one is let you to get used to the notation first. Okay, so first it said resistance R and the sinusoidal AC device operate at amplitude EM equals 36 volt and frequency FD equals 60 Hertz. What is the potential difference VR across the resistor as a function of time T, and what is the phasor VR? Okay, so yeah, so let me see. So VR. Okay, VR, okay, I use small letter of V to represent this is a time domain function. Okay, I say this is a time domain function. Time domain function. 一个时域的函数. Okay, so this is, yeah, this is 36. So this is also 36. And then cosine of 2 pi times FD is 60, so 60.0 T. Okay, so this is something like this, and you may somehow simplify it. 36 cosine of 120 pi T. Okay, and then the SI unit is volt. Okay, so this is the potential difference V out of T. Okay, and then the phasor, for the phasor V out is nothing but 36 volt. Okay, so for this one we don't have a phase. Okay, you consider the phase phi is 0 here. Okay, I don't write degree, but you should use radian here. Okay, so this is actually like 36 exponential to J0. Okay, and this one is nothing but 1. So this is 36. Okay, so this is why VR is 36. Okay, not only taking this number, but also consider the phase. Okay, although this is just a resistor, so all the things will be a real value. So you don't see what is going on here. Okay, for the question B. Okay, it's ask you what is the current IR in the resistor and phasor. Okay, so for the IR of T is nothing but VR of T over R. Okay, V equals IR. So for the resistor, so this is very trivial. 36.0 over 200 ohm, and then cosine of 120 pi T. So this is nothing but 0.180 cosine 120 pi T. Okay, and the SI unit is A. Okay, so this is also the time domain function, the current. Okay, and then for the phasor, IR will be 36 is nothing but 0.180. Okay, also taking this value and also the phase here 0. Okay, this is the phi. Okay, so exponential to J0. So this is the phasor. Okay, so for the resistor, all the things is quite trivial. Okay, so now we consider another sample problem about the capacitor. So the only difference is that we change the resistor into a capacitor. So C is 15 μF here, and then all the other conditions are the same. So it just asks you what is VCT, and then also what is the phasor VC. Okay, so here VC is actually EM. Is nothing but 36.0 V. Okay, so this is still the phasor here. Because yeah, we just have this is EM and then cosine of 120 pi T. Okay, so for the VC, the phasor for the voltage across the capacitor is actually the same. Okay, so the voltage here is still EM times cosine of 120 pi t. Okay, so the phi here is still 0. So the phasor VC is still 36.0 volts. Okay, so and then actually VC of t is still 36.0 cosine 120 pi t. Okay, so this is still very trivial. Still very trivial. Okay. So for the question B, it asks you what is the current IC here and also the ICT. Okay. So here, okay, so ICT is a time domain function. Actually, you can, if you like it, you can use IC of t equals CD VC dt, something like that, to take the derivative of the VC and then you get IC. Okay, but here we don't want to use the derivative. Okay, we just want to compute some complex number to get the answer. So here IC is actually J omega C VC. Okay, so this is this is related to the impedance. If you couldn't remember, I just recall it a bit. This is the impedance of C equals 1 over J omega C, which will be the phasor of C, the phasor of VC over the phasor of IC. Okay, so just move IC to the left side, move J omega C to the right side. So we have IC equals J omega C VC. Okay, you consider this is 1 over CC. Okay, 1 over CC. So J omega C VC. Okay. So here we have a J and then omega. Omega is this one. Okay, this one is the omega, 120 pi. 120 pi is the omega. So 120 pi. And then C is 15 times 10 to negative 6. And then VC is 36.0. Okay. Like this. So this is nothing but J 0.203. 0.203. Yeah, J 0.203. If we forgot what is J, J is square root of -1. Okay, I used to use J rather than I. Yeah, because we already use I for the current. Okay, so I always use J to represent the square root of -1. Okay, so as much as we have this is the phasor. This is the phasor of IC, but actually we can write it in the polar form of the complex number. So this is nothing but 0.203 exponential to J pi over 2. J pi over 2. Or actually, we should give it a SI unit. Okay, so this is A. Okay, this is a current. Okay, A. Okay, how to get it is that if you can remember, okay, actually this one is actually J. This one is actually J. Or the geometric meaning is that, okay, so for J 0.203 is like this is the real axis, this is the imaginary axis. Okay, and this is J, so this is J 0.203. Okay, and then okay, so the distance here is 0.203. Okay, which is this one, and then this angle is pi over 2, 90 degree pi over 2. So this is the angle from x-axis to this point, and then this is the magnitude. This is the magnitude, or this is the absolute value. This is the absolute value of the complex number, and then this is the angle. Okay, so in this case, IC of t equals 0.203. Okay, so this is the magnitude, goes to here, and then cosine of 120 pi t, and then plus this angle. This angle goes to here. Okay, pi over 2. Okay, this one, this 0.203 goes to here. Okay, and then A. Okay, so this is a time domain function. If you don't believe, you can try to plug in this Vc of t to here, then you will get the same result. You'll get the same result. Okay, so this is the sample problem for the capacitor. And we also have another one for the inductor. Okay, so for the first one is also ask you what is VLT. So VL is nothing but 36.0 volt. Okay, just as before. Okay, VL of T is nothing but 36.0 cosine 120 pi t volt. Okay, so actually the same as the previous two. Okay, so for this one, okay, we have it asks you what is ILT, okay, but if you don't try to use the phasor, okay, we should have something like VL of t equals L dIL dt. Okay, here we know the VL of t, so you need the integration. Yeah, so this is not a great move. So here we also try to use the phasor. So actually the phasor is like IL equals VL over the impedance of inductor, which is J omega L, So this one, J omega L is ZL, so V equals IZ, okay, V equals IR, V equals IZ, okay. So this is 36.0, and then over J, omega is the same, 120 pi, and then L is 230 times 10 to the negative third. Okay, so this is nothing but negative J 0.415. This is A, or if you would like to write it in the polar form, it would be 0.415 exponential to negative J pi over 2. A. Okay, so this is a negative J something, so which means this one is here, negative J 0.415. Okay, so this is negative pi over 2. Okay, so this is the magnitude here, and then the angle here. Okay, so in that case, IL of t will be 0.415 cosine of 120 pi t minus pi over 2 a. Okay, so this is a time domain function. If we make use of the phasor, yeah, of course there are some math. We need to compute the complex number. Okay, but it is only some algebraic calculation. 就是它只是一些代数的运算。如果它给你一些数字的话，你带进去一些数字，它就变成一个复数，它就是一个数而已。那但是这个数可以去表达一个sin 啊，它 sin 的一个正负跟相位啊，它就可以决定一个正弦波啊。那算完这个之后，我就把对应的数字放回来，它就是那个time domain的结果，我们就不需要去算那个微积分。Okay, so far any questions? Okay. So here we talk about the series RLC circuit. Okay, you may say, we have already learned our damped RLC, damped oscillation. Okay, what is the difference? What is the difference? So here, take a look at this. We have RLC in series. Okay, so the order doesn't really matter. You may put RLC here like that, or LCR, whatever order. It is almost the same. Okay, yeah. So, but here we not only have RLC, we also have this AC source. Okay, we also have this AC source. So this is the main point here. Okay, and then compare with the previously the damped oscillation. For the damped oscillation is here we only have RLC in series. We don't have any source. We don't have any source. We only assume that there are some energy stored in either L or capacitor, L or C, or maybe both. Okay, there are some energy stored there, so that there will be a so-called a damped oscillation, and then the energy will be consumed by the resistor. So the oscillation is somehow like this. Okay, but here when we consider this series RLC circuit, okay, just as last time I mentioned, here we would like to consider the steady state response. Okay, we would like to consider something called a steady state, where I mentioned that maybe, yeah, we would like to consider the steady state, which means if you like, you can also write a second order ODE to describe the series RLC circuit with the AC source, and then you try to solve for the complementary solution, and then later on the particular solution, add them together, and then you plug in the initial condition to find the complete solution. But this procedure is quite tedious. Okay, and also if the circuit is stable, the complementary solution always tends to 0 for T is large. When T is large, the complementary solution will decay to 0. So, and in that case, we usually only consider the steady state, which means about the sinusoidal related to the input. Okay, so this is the quick shortcut that we only focus on the steady state, and then in that case, using this kind of phasor, okay, using the phasor to analyze this RLC circuit, we can skip all the procedure for solving the second order linear ODE. Okay, we just need to compute some complex number, and then using this complex number, and then we can just convert it back to a time domain function, so that we don't need to solve the second order ODE. Okay, so the only problem is that we need to understand what this is going on here. Okay, so here we have a RLC circuit with RCL like this, and then with AC source. Okay, we also assume the AC source is E equals Em cosine of omega dt. Okay, so still the same as before. And then here we have the I to be capital I sine of omega dt minus phi. Okay, and okay, so this is I here equals to this stuff. Okay, so why we like that? So here on the right side we have RLC in series. So which means if they are in series, we can use the series formula for Z equals CR plus CL plus ZC. Okay, so we just for series impedance, we just need to add them together. If the impedance are in parallel, then we need to use a reciprocal and then add them together, take the reciprocal again. Okay, 所以这里要注意一个是，之前如果我们只看电阻、电容、电感的话，它们分成两组。电阻跟电感的话，串联是加起来，并联的话是取导数加起来再取导数。电容的话是反过来的，串联的电容的话是导数加起来再导数，然后并联的话是加起来。那这里 impedance 的话，串联就加起来，串联就加起来。 So here we have a CR plus CR plus CC. Okay, we have series RLC, so we add the three impedance together. So the impedance of R is nothing but R, and then the impedance of ZL is J omega L, and then for the ZC is 1 over J omega C. So if we put this J to the top, okay, we have J squared equal to -1. So we have a negative J over omega D, negative J over omega D here because ZC is 1 over J omega C. Okay, if you multiply another J, another J, so it becomes J squared is -1, so negative J over omega C. So like this. Okay, so if we collect together, okay, the real part only related to the resistance, and then the imaginary part related to both the inductor and the capacitor. 而且你看这个的话，你就会容易明白为什么这里电容也是加起来就好，就是因为它 impedance 里面已经有一个倒数在，所以它已经倒过一次，所以它就倒完之后，所以在 impedance domain 里面RLC 的地位就一样它们只是变成说J omega L 是一个正的虚数或者是有一个正的虚部吧那电感的话是有一个负的虚部Okay, so if you can accept this one, okay, so this is the overall impedance of this RLC in series, then we can know what is going on here. So actually, this part is like the impedance of I will be E. Okay, so this EM is like a voltage, the phasor of the voltage. Okay, over the absolute value of C, the absolute value, okay, 绝对值 absolute value of C. So absolute value of C, how to take? So this is the real part, this is the imaginary part. So the square of the real part, so R square, and then the square of the imaginary part, okay, here, and then add them together, take the square root, is actually the absolute value, okay, or if we have a Z equals A plus JB, okay, absolute value of C will be A squared plus B squared, and then take the square root, something like this. Okay, so here we have the phi, okay, so we have the phi, okay, because we still have the phase shift here. The phase shift here is nothing but taking the imaginary part over the real part, and then equals to the tangent phi, Yeah, because it is nothing but if it is like Z, if you have a Z equals A plus JB, okay, in the coordinate it would be like this is A plus JB, okay, so this is A, this is B, okay, so this phi is nothing but tangent phi will be B over A, okay. Why not saying phi equals arctangent of this stuff is that if A is negative, we need to add a pi to it, okay. 就是如果它是 A 是正数的话，它在D4上限的话，那 arctangent of 这个东西就没有问题。但是如果 A 是负数的话，你说为什么电阻会负数？它可以存在的，但是在这里的话应该不太会出现。所以你真的在这里要写这个的话，其实也是可以也是可以的。但是如果 generally 的话，也许有可能出现负的电阻的时候，那万一 A 是负数的话，那这个 arctangent 加派才会是这个东西。Okay, so this is the phi. Okay, so according to the phasor, we will know why this the phasor of the current will be like this. The phasor of the current will be like this. So in that case, we only if we have the number EM, R, L, C, and also the omega D, we just plug into it, and then we just calculate this is the magnitude. This is the magnitude of I, and then this is the phase of I, and then after computing these two numbers, okay, the solution is nothing but this. Okay, so this is very very trivial. And then here, different from the damped oscillation, we have this omega d to be 1 over square root of LC. This is the oscillation, the resonance, okay, the resonance, 中文叫做共振嘛，共振。Okay, so the condition meets when the imaginary part is 0. When the imaginary part is 0. Okay, so this part equals 0. This is the resonance. Resonance 共振。为什么？它的意思是这个什么时候可以最大 ？So the when is this phasor take the maximum? Okay, which means the magnitude of the current to be maximum. Is that okay? So this is a positive value. Okay, we can't do anything to it, but we can choose an omega d such that this one can be a 0. Okay, if this is a 0, okay, because we have a square here. Okay, if we can take this to be 0, then the denominator will be minimized, so the whole thing will be maximized. Okay, 就是我们想把这个振幅，这个电流的振幅取到最大。最大的话，EM 不能动 ，R、LC 都不能动，那我们只能找一个omega d 出来，omega d 出来，让这个部分或者是这个 impedance 的序部为0啊，这个为0的话，那这一个为0的话，那分母就会最小，分母最小的话，整个会最大。Okay, so the condition is like omega d L minus 1 over omega d C equals 0. So by solving it, we can easily find that this is nothing but omega d equals 1 over square root of LC. So this is different from the damped oscillation. Yeah, for that one, okay, the natural frequency is a little bit smaller than this omega. Than this omega. 那个情况的话是因为没有输入，所以它的自然频率被那个电阻拖慢了，所以它就会那个自然频率会降低。但是这个的话，因为是有源的，有电源的有一个 AC source 在这里，那你有 AC source 是这个频率的话，那你的电路的震荡也是同一个频率。那在共振的条件的话，就是这个，就是1除以派根号 LC。Okay, so yeah, so actually, okay, so in the textbook it just tell you the idea using the phasor, okay, and then you get this result. Okay, if you don't believe, you can also try to use the potential method, okay, to write the ODE, okay. So actually this E is nothing but EM cosine of omega dt, and then I assume this is VR, this is VC, and then this is VL, like this, okay. So plus minus, okay, back to back, so that we just add our VR, VC, VL together to be this E. So we have an EM cosine of omega dt, okay, I don't need these parentheses, okay, equals VR plus VC plus VL. Okay, so this is the KVL. Okay, so VR is nothing but R times I, and then we have VC. VC is VC. Okay, and then VL is LDI dt. And then we also have I equals CdVC dt. CdVC dt. Okay, so we need to, okay, I also copy it down so that for the whole thing, we try to take the derivative and then all multiply by c, okay, because I would like to construct this one like this. Yeah, here we only have vc here, so if we take the derivative, it becomes a dvc dt and then multiply by c, okay, this term will become the I, okay. So for this stuff, okay, taking the derivative becomes negative omega d em and then sine of omega dt, okay, and then also multiply by c, okay. So maybe I put this here, omega dc and then em, something like this. Okay, so here we have a di dt and then rc, and then this one is c dv dt, which is I, and then we have lc d2i dt2, okay, and then we can try to normalize it by dividing lc on both sides, so we have a d2i dt2 plus r over c, r over l, and then di dt, and then plus 1 over lci equals negative omega d em over l, and then sine of omega dt, okay. So this is the second order constant coefficient ODE governing this circuit. Yeah, if you really need to solve it, then first of all you need to solve for this homogeneous solution, which is like s squared plus RL times s, R over L times s plus 1 over LC to be 0. Then you will get S1, S2. And then we also assume that this R over L squared minus 4 over LC is smaller than 0 to guarantee it is an oscillation. Okay, and then we will get the complex number, the complex value for S1, S2, and then we can write out the complementary solution. And then you can also, according to this one, to let the IPT to be A sine of omega dt plus B cosine omega dt, and then we plug in this one back to here to solve for A and B. So this will be a very tedious job. And then yeah, we will have quite a lot of variables to really solve that. So if your calculation is correct, you will find A, B. Okay, we will something like we will have something A and B, and then by taking A squared plus B squared and then take the square root, it will be this stuff. It will be this stuff. And then if you take let's say A over B will be like this. Okay, so if you have interest, you can try it by yourself. Yeah, I don't try to go through. I just let you know that if you don't understand why it will be like that, okay, of course it is according to the phasor, and then behind it is related to the Fourier transform. But if you want another way to understand this kind of strange formula, this is according to this. You can always try to write as second order ODE governing this, and then you try to solve, and then you will find actually the same solution to this one. Okay, so that's why we need to teach the phasor, because doing this stuff is very, very tedious. Even I don't want to go through it. So using the phasor will be a good alternative. We just need to plug in the number. If we have EMR, LC, and also the omega d, or just plug in all the number or to get I, and then also get this phi, and then it's already done. Okay, so this is why we will like to learn it. Okay, so maybe the mathematics is still very complicated to use. So let's take a look at this sample problem. Then you'll find it is not that difficult. Okay, so here we have RLC and also FD. Okay, not omega d. So omega d is 2 pi FD. And then we also have this EM. Okay, so what is the amplitude of the current phasor? Okay, so yeah. Okay, so for the first step, we would like to write out the impedance of the RLC. So which is nothing but R plus J and then 1 over J. J omega d L minus 1 over omega dc. Okay, so this is the impedance of the RLC, series RLC. So R is 200, and then J, and then omega d. Omega d is this one is 60. So omega d is 2 pi FD, which is 2 pi times 60, which is 120 pi. Okay, so this is 120 pi, and then times L is 230, and then times 10 to negative third, and then minus 1 over, this is 120 pi, and then C is 15 times 10 to negative 6. Okay, so this is 200 minus J, and then 90.13. Okay, yeah, this is not difficult. Just put in the calculator to press out this stuff is 90.13. So yeah, this is okay. And then if you like, the SI unit is still ohm. Okay, the SI unit for the impedance, we still write it as ohm. Okay, so for the I is nothing but EM. Okay, we don't take the absolute value yet. Yeah, because we would like to have EM equals Z, EM over Z, which is 36.0 over 200 minus J 90.13, like this. Okay, so actually, maybe for some of the calculator, you can directly compute this one to be something plus J something, okay, or I something, something like this. You can do it, yeah. But if we would like to compute the absolute value of I, the absolute value of I will be nothing but the absolute value of the numerator divided by the absolute value of the denominator. OK， 就是如果你有一个复数的乘法或者除法，他们要去求这个绝对值的话，绝对值的话，那乘法除法的话，你可以先各自取完绝对值之后再乘起来或除。对，那这里的话就是除嘛，所以这是36的绝对值是36 36.0 over the absolute value of the denominator is 200 square plus 90.13 square, and then take the square root. Okay, yeah, actually negative 90.13 square. Okay, but negative square is still 1. Okay, so this is nothing but 0.164a. 0.164a. And then for the phi is nothing but arctangent of negative 90.13 over 200. So this is nothing but negative 24.3 degree. Negative 24.3 degree. Or if you like, you can write it as negative 0.424 radian. Okay, radian. Okay, so actually the amplitude in this question is this one. Okay, so the amplitude is 0.164, and then the phase. The phase is actually arctangent negative 90.13 over 200, which is negative 24.3 degree. Okay, or negative 0.424 radian. Okay, so this will be quick. And if we already have this, we can directly write out IT to be I is 0.164. Although the question doesn't really ask you, but according to the formula before, okay, so omega d is 120 pi t, and then plus or minus minus 5. Minus 5 is negative, so this one becomes plus 0.424, 0.424, something like this. A. Okay, like this. So we don't need to solve for any ODE. We don't need to even write out the ODE. Okay, but using the phasor, we just play with the complex number. Okay, and then we can directly get the result for the steady state response. Okay, of course, it's only the steady state response. Very important point is this is only the steady state, not the complete solution. Not the complete solution. Why the complementary solution doesn't really matter here is, the complementary solution will tend to 0 when t is large. So we usually only focus on the steady state, which only relate to the input or actually this AC source. Okay. So any questions? No one, right? Okay, so if no question, then we can move forward. So let me finish this page. So here we talk about the power in AC. So for power in DC, okay, previously we learned most of the stuff in DC. So for that part, we have P equals I times V. P equals I times V. Okay. If the source is DC, okay, we just multiply the I and the V together. We have the power. But here the situation are a little bit different. The idea here is like this is a sinusoidal. So actually you can still write it as P of t to be I of t times V of t. So in that case, we call this one the instantaneous rate or instantaneous power. 这是一个叫做瞬时的功率，就是每一个时刻的它的功率，有可能在某些时刻是负的都有可能是有可能的如果它有 LC 存在的话，它是有可能是负的，瞬时的话，但是平均的话它还是会正或者是至少是0的Okay, so this is the instantaneous rate. So the instantaneous rate is like this is a square of a sine. Okay, so because previously we already know that I is this absolute value of I and then times sine of this stuff. Okay, so if we have I square, so we have this absolute square and then sine square and then multiply by R. So this is the instantaneous power dissipation. Okay, but this is a sinusoidal square. Okay, but of course it is still a sinusoidal, something like this. Okay, this one is the sine square. Okay. 但是我们想知道的是一个平均值会好一些，因为它有时高有时低，那我怎么去理解这个有时候功率大有时候功率小呢？那我就取个平均，但是平均的话就是功率可以平均，但是 电压不能平均，电压平均的话 sinusoidal 平均就变成0，所以我们不能够说这个取个平均，这个取个平均乘起来它就变成0，因为两个 sin 它说就算是不同相位，它整个平均完之后就比如说这个平均一个周期平均有一半是正的，有一半是负的，平均没有，什么都没有，那就不可以。那功率的话，我们是可以做这个事情。Okay, so here the idea is like, so we have the P average. P average will be like this. This is the result. Why it is like this? So P average is actually like this integration. This integration, or okay, not this one. Okay, not this one. Sorry. So the integration, I mean the P average. The P average should be okay. This is I say this is P of t. Okay, so this is like an integration of P of t dt, and then from 0 to capital T. Okay, so this is the period. 这个是一个周期，积分一个周期。因为它是周期函数嘛，所以我积分一个周期，算它周期内的平均就 OK 了。那几个周期的平均其实是一样的。Okay, so we integrate the power for a period and then divide by the period. 就是好像你比如说全班的平均分数，就是全班的分数加起来，然后取人数就是这样。但是这个是连续的嘛，所以我们用积分去加，积分加积分一段时间，然后除这个时间长度，那就是它的 P average. Okay, so for the P average, integrating this stuff, okay, so this is a constant. This is a constant with respect to the time. Okay, so I mean this I square out is a constant with respect to time, so we can put it outside. Okay, and then finally, what we need to care about is this sine square. So here we try to consider this stuff, okay, which is part of the P average. Okay, we can consider this is P average divided by I square out. Okay, so this is like this. Okay, so integrating this stuff is not difficult, but the only point you need is you need to know sine square of x is 1/2 of 1 minus cosine of 2x. Okay, or cosine of square x equals 1/2 of 1 plus cosine of 2x. You need to know this. Okay, you need to know this. So in that case, sine square, okay, we have a 1/2 go to here, 1/2 go to here, and then inside the integration we still have 1 minus 2 times of this stuff, so that we can get rid of this square. Then we can do the integration. So doing the integration for this one from 0 to t is nothing but t. So this t and t will cancel, becomes a 1/2. And then for this one, of course, it becomes a sine of something. But integrating a cosine 2x for 2 periods, actually for 2 periods of it. One period of it is actually like 2 periods of it. So in that case, integrating this stuff will become a 0. So it is like 1/2 plus 0 equals 1/2. Okay, so finally P average is like 1/2 of this stuff, which is this equation. Okay, so the point here is if we have the DC, okay, P equals IV, and then if it is for a resistor, it is nothing but I square R. But here we have I square R over 2. Okay, so if we don't define something called the root mean square value, then sometimes we need to know, oh, this is for DC, we don't have this 1/2 vector. And then for AC, we need to put this 1/2 vector. Then, okay, they don't like this. They don't like this. They don't like still the P with two different versions. One with 1/2, one with 1/2, one without the 1/2. Okay, so they try to define. They try to define something like this. Okay, so for this one, we just put these two inside this square. But here we take the square root of 2. Take the square root of 2 square. So it turns out to be a 2. So it doesn't change anything. So here we try to define this stuff. Okay, this stuff to be I RMS square. Okay, so this stuff becomes I RMS square R. Okay, so now we have a I RMS square R, and then we have a I square R. This one for DC, or this one for AC. Okay, they both have the same form. Okay, so they are happy at this stage. So which means we should have this IRMS to be I over square root of 2, or also V RMS to be V over square root of 2。所以就是有这个叫做有些叫均方根，有些叫方均根，我都不知道中文叫什么，反正就是 root mean square 看你要排哪个在前面嘛，这个是根嘛，这个是平均嘛，这个是平方嘛，所以根均方方均根，我不知道叫什么好，中文我不知道，反正英文的话永远都叫 root mean square。Okay, so yeah， 所以的话就是说，如果是一个如果是正弦波的话，正弦波或者是交流电的话，他们很常会用这个叫做 RMS value， 而不是用振幅，比如说我们澳门的交流电220伏。220伏是 RMS value RMS value， 所以它的振幅是300多你乘一个根号2上去是300几，我忘记是307还是多少对，所以是通常他们会直接用这个root mean square 去说因为如果我要知道的话，就是你的比如说 V 是220伏，那我就知道直接用 V 平方除以 R， 我就不需要管说直流交流，但我如果知道电阻的话，V 平方除以 R， 无论你是直流交流，它都是这么算的，它就不会有任何误会，差了1倍。Okay, so let's have